water, that is, when you have a sample of pure water, it actually deprotonates itself. So a proton transfers between water molecules, and you get a small amount of ions. And that small amount of ions is enough to be a measurable concentration of hydronium ion. And we said the hydronium ion and the hydroxide ion concentration are equal in that pure water. And the product of those two is a constant that always stays the same, which means if the hydronium ion and the hydroxide ion change, they always compensate for each other. So an increase in hydronium ion leads to a decrease in hydroxide ion and vice versa. So they're always balanced. And we mentioned that these numbers are really small, and because they're so small, they're always expressed using this scientific notation. So hopefully you had a chance to practice that and get a little bit more comfortable with that. But one thing we want to do is, since this is important and it's kind of central to acid-base, it is annoying to have to use this scientific notation all the time and write all these tiny numbers with their exponents and whatever. So that's why this pH scale was developed, to actually convert from this stuff to something that's a little bit more manageable. So let's look at that. pH is actually something that you get from the hydronium ion concentration. So you do a calculation from the hydronium concentration and you get the pH. And here's what the calculation looks like. So it's the negative log of the hydronium ion concentration. And as I said, this is the last math we're going to be doing, pretty much. Actually, yes, it's the last math we're doing in the class. After this, it's organic chemistry, biochemistry. So you got to hold it together for like one more day, and then we'll be done with it. So who knows what logs are? Yeah, that's about what I expected. Have you ever done it before? A long time ago? So if I was like, hey, take the log of a number, what would you do? Yeah, you just use the button on your calculator, right? So it's not that scary. It's just a calculator button. And actually, that's not really far from reality. You can't calculate logs without some kind of a reference, either a calculator or in the old days they used something called log tables, which is just like you had to look it up on a table. Because logs are a little tricky to calculate. What they do is they give you the exponent. So in general, a little bit of log review. A log of 10 to some exponent returns the exponent. So when that's a nice even number, that's really easy to do. You just look at whatever little number is up on the exponent from 10, and that's your result of the log. So if we take hydronium concentration of 1 times 10 to the minus 7 molar, all right, and we want to take we want to get the pH of that, what the equation tells us is we have to take the log of that, and then we have to take the negative of it. So we take the log, and then we flip the sign. So the log of 1 times 10 to the minus 7, since that's a nice even exponent, 1 times something is just the something. So we can think of that as log of 10 to the minus 7. That's just going to be minus 7. You don't need calculators or anything for that. It's just the exponent. So then if we want to get the pH, we take the negative of that log, which is just flipping the sign because the negative of a negative is a positive. So think about what we just did there. We calculated this new thing called pH using the hydronium concentration that actually is the hydronium concentration for pure water. And we came out with the number 7 as the pH. So 7's a lot nicer of a number to deal with than 1 times 10 to the minus 7. So that's what this is for, to give us that kind of nicer scale. So what do you know about pH 7? Anybody had experience with pH before? It's neutral, yeah. It's right in the middle of the scale. So if we have a solution with pH 7, we're saying that this has the same hydronium concentration as pure water. Therefore, it's neutral. So we kind of set that to the middle of the scale because that's the concentration of hydronium in pure water. We can also define a POH with the exact same calculation. We just plug in the hydroxide concentration instead of the hydronium concentration. So let's say our hydroxide ion concentration is like it is in pure water, also 1 times 10 to the minus 7. So it's going to be, what's the POH going to be then? We have that same concentration, we're doing the same thing. It's going to be 7, yeah. So that'll be also the negative log of that same value, which is 7. So if we go back up to this equilibrium constant for water thing, we say that these two multiplied together always equals 1 times 10 to the minus 14. But another way that we can say that is that the pH, which is the negative log of the hydronium concentration, plus the POH, which is the negative log of the hydroxide concentration, is always going to be 14. So that's another way of saying that same thing. The concentrations multiplied together is 10 to the minus 14. The P's added together is 14. So with that information, not only can we calculate pH from hydronium concentration, but given any one of those things, pH, POH, hydronium concentration, or hydroxide concentration, we should be able to calculate the other 3. So let's try that. So let's say we have another solution where the hydronium concentration this time, and we're not going to use such nice numbers this time. Let's say it's 3.2 times 10 to the minus 4 molar. So that's our hydronium ion concentration in solution. Knowing that, we can calculate the hydroxide concentration, the pH, and the POH. So let's do that. The easiest thing to get from the hydronium concentration right away is the POH, or the pH, sorry. We can just plug it in the equation. pH equals negative log of the hydronium concentration, which in this case is the negative log of 3.2 times 10 to the minus 4. All right. So let's do that. Now, depending on what kind of calculator you have, this can be easier or harder, whatever. On quizzes and exams, you will not have to calculate these kinds of numbers because we don't require that you have a scientific calculator in this class. But you will run into it in the homework and in some of the lab stuff. So we're going to practice it anyway. Some, like the graphing calculators, make this a little bit easier. If you have an old style scientific calculator, it makes it a little bit trickier, but let me show you how it works in case you're using that type of calculator. And I think some of the phone calculators work this way too. So on these types of calculators, you can't just type it in from left to right the way you would on a graphing calculator. So you can't just type in negative log parentheses and then the scientific notation. You actually have to work from the inside out because each thing is an operation on that that previous thing. So let me show you what that looks like. So I actually start here, whoops, not with the 1. I start at the exponent here, that minus 4. So I type in 4, I make it negative, then I raise 10 to that power. That's what that little button does. Then I multiply the 3.2, So that's my inside number now, 3.2 times 10 to the minus 4. Then I can take the log by clicking log. That's my log. And then I can flip the sign with that plus minus key. So I get 3.49. If you want to know how to do this on your specific calculator, just let me know at some point during lab today or something. I can show you how to do it. So that's our pH. All right, so if the pH is 3.49, what is the pOH? How do we figure that out? Yeah. Yeah, we're going to subtract from 14 because the pH plus the pOH have to equal 14. So 3.49 plus what number is 14? Well, that's not too bad to figure out. 14 minus 3.49 is 10.51, right? Yeah. All right, so we got the pOH. Not too bad. So then our final step is to get the hydroxide ion concentration. There's a couple ways to do this. You can get it from the pOH, kind of doing the backwards calculation of the negative log calculation. Or you can go back up and get it from solving this for the OH concentration. So you plug in your hydronium concentration here, and then divide this by that number. Let's look at both ways of doing that. So if the pOH is the negative log of the hydroxide, does anybody know what the opposite of a log is? Like, what do we do to this side to cancel out the log? Come on, algebra fans. No, nobody? It's been too long. Close. You're just throwing different calculator buttons out there. Getting there. It's something. Another good guess. I guess I'll just tell you. It's the 10 to the whatever. So you raise the power to that. So we'll go back to our little log review here. Log of 10 to the x is x. 10 to the power of a log of something is just that. So log and 10 to the are inverse operations. So what that means for us is if we want to calculate the hydroxide ion concentration, that means we take the pOH and we raise 10 to the power of the pOH. Sorry, the negative, because it's a negative log. So that would be 10 to the minus 10.51. And that would be a molar concentration. Now, normally we don't leave exponents in that, or scientific notation in that form. We actually evaluate that so that we have an integral exponent. If you don't have a calculator that can do this, you can totally leave it like that. That's fine with me. But if we want to actually calculate it out just to see, we would go 10.51, take the negative, and then take 10 to that power. And we've got 3.09, and this little e minus 11 means 10 to the minus 11. So that means that our concentration is 3.09 times 10 to the minus 11 molar. That's the hydroxide concentration in this solution. So given the hydronium ion concentration, we were able to calculate the hydroxide concentration and the pH and the pOH. All right, so now it's your turn to try it. So these are the 4 interrelated variables: the hydronium ion concentration, the hydroxide ion concentration, pH, and the pOH. And so if I give you one of them, like if I say the pH is 10.2, or if we say the hydroxide concentration is 5 times 10 to the minus 2 molar. See if you can fill in the rest of these. So using those same techniques, calculate the rest. Every calculator that you're supposed to need. We don't need calculator help or other help. No, that's just what goes back. If you get some of these numbers, talk to the people around you, see if your numbers match up. If not, talk about what's going on there. All right. Everybody got something? Take another minute or so. I see some people still calculating. We'll look at it. All right, so I'm going to go through these calculations with you. If we're given the pH, probably the easiest thing to calculate next is the pOH, because that's just the one where you subtract from 14, right? So the pOH then is going to be 3.8. And then from there, we can calculate the concentrations by raising to the power of 10, the negative to the power of 10. So we would go for the pH, or I'm sorry, for the hydronium ion concentration, we take the pH, which is 10.2, take the negative of that, and then subtract from 14, because the pH and the pOH always have to add it to 14. pH and pOH have to add up to 14 always. So if we have one of them, we get the other one by subtracting 14. All right, so then we take that, make a negative of it, and raise to the power of 10. And we get 6.31 times 10 to the minus 11. And that's a molar concentration. All right, so for the hydroxide concentration, we can do the same thing with the pOH. It's probably the easiest way to go. Take 3.8, make it a negative, raise 10 to that power. What was it? 4. Okay, same idea. Yeah.
Remember how you got that H3?
Yeah. So let's write it down here. So if the pH is the negative log of the hydronium concentration, let's go through the algebra here. So normally, you'd like solve for that and you divide by whatever other stuff. So we have to kind of undo a log. And the way that you undo the log is with that 10 to the power. So first we get rid of the negative by multiplying both sides by -1. If we multiply by both sides by -1, we get pH equal, or negative pH equals the log of the hydronium concentration. Then we can raise both sides 10 to the power to a power of 10. Because 10 to the power and the log cancel each other out. So that's how we get the hydronium concentration.
So you do 10 to the negative 10 to the power?
Yep. And that's how we got 6.31 times 10 to the minus 11. And you could leave it in that form, 10 to the minus 10.2 power. Also, if you didn't have a calculator that could solve that. All right. Let's continue with the next one then. So from the hydroxide concentration, we can get the pOH, again, by taking that negative log. So we've got 2, -2, 10 to the -2. So that's 5 times 10 to the -2. If you know your scientific notation, you may also just see that as 0.05. You can type that in too. And then we want to get the negative log, so we take the log of that, and then take the negative of that, get 1.30. 1.30. For the POH, we're going to subtract from 14 again. So that gets us 12.70. Or I guess 12.7 really is, you can leave it. And then we need to get that hydroxide ion concentration, or I'm sorry, the hydronium concentration. So we take 10 to the minus 1. Oh. Phone's mad about something. It's running low on memory. All right, well, just gonna turn it off. I'll use this thing instead. So take 10 to that power, we would go 1.3. Take the negative, raise 10 to that power, and then oh yeah, so that's it. So that's going to be, whoops, hold on, I got these switched. Did anybody notice my mistake here? Yeah, so remember this, what's given here is the OH concentration. So these should be switched. We did all the calculating right. We just named it wrong. So let's try that again. We'll take 12.7, negative, raise to the power of 10. And that looks better. So we've got 2 times 10 to the minus 13 molar. We took this number and subtracted from 14. Well, we were given this number, and from that we can solve here by taking the negative log, hydroxide to POH. Once we have the POH, we get the pH by subtracting from 14. These two numbers always have to add to 14.
So you just put in the 5.0.
Yeah, I put this into the pH or the POH equation here to get that, to get 1.3. Yeah, Andrew. So, good question. So I will not make you do these kinds of calculations on the test because you may not all have calculators that can do it. So what you should be able to do is that, but with nicer numbers. So let's try it one more time with nicer numbers and see if you can do it in your head without using a calculator. And then if you want to use a calculator, you can check it. All right, so let's say I tell you the pH is 4. Can you calculate the rest of those from there? Give it a try. All right, so hopefully we are getting the same numbers here. Again, the pH and the POH have to equal 14, so the POH has to be 10. Now to get the concentrations, since we have nice even numbers, we don't have to do any calculations. We can just raise them, take the negative, and then raise it to the power of 10. So the pH goes with the hydronium concentration. So instead of 4, that's going to be 1 times 10 to the minus 4 molar. See what we did there? We just put the 4 up on top and made it a negative. For the hydroxide concentration, we do the same thing from the POH, which is put the 10 up there. Notice that's nothing different from what we did up here. The only difference was we evaluated that, that 10 to the whatever expression using a calculator instead of just leaving it in that form. When the numbers are nice and even, we just leave it in that form. That's the only difference. All right. Any questions about that? So let's take a look at this new scale we've constructed, this pH scale, where we said that 7 is going to be in the middle. And then, well, you tell me, if the pH goes lower than 7, what does that tell you about the hydronium concentration? It's acidic, so what does that tell you about the hydronium concentration? It's higher. So that's why the pH scale kind of seems backwards, that the lower numbers are more acidic, because it really is referring to an exponent, a negative exponent. So lower numbers are actually bigger when you calculate the hydronium concentration. So there's more hydronium concentration in acids than in bases. Let's take a look at this. From the, there's a picture in the book here that tells us a nice scale, a nice picture of the pH scale. I'll paste this and then we'll kind of zoom in to look at it a little bit closer. All right, so here, this tells you everything except the POH, but you've got the hydroxide concentration, the hydrogen, which is also the hydronium concentration, and then the pH. At very, very low numbers, you're talking about extremely acidic things. So if you have about, let's see, what would that be? Not concentrated hydrochloric acid, but some of the solutions that we've used in lab of hydrochloric acid are way down at 0. You got stuff like stomach acid at 1. Most of the stuff that's tasty is right around this 3 area, 3 to 4 to 5. A lot of our foods, we mentioned this before, but a lot of our foods are acidic. It tends to taste good to us because we can taste it with our receptors. It's kind of sour. So especially sweet things like candies, but also sauces and, you know, tomato sauce, that kind of stuff, all is in that range. That's one reason that that stuff is all bad for your teeth, is that your teeth start to break down, decalcify at about 4, pH of 4, 4.5. So anything below that puts your teeth in the state that the enamel starts to break down. And if that breaks down, then that can allow bacteria to grow in there. That's also why things like juices and sodas and sweetened coffee and things like that are especially bad for you, because then it's compounded with sugar, which the bacteria can feed on. Yeah. You know, I don't think that's quite true. That's a really high number for black coffee at 5. That really depends on the type of coffee. There's actually a pretty big range of acidities in coffees. So I don't think you can quite be like, no, coffee's fine. I think most dentists would tell you that coffee is still not great. But for sure, black coffee is way better than coffee with milk or sugar that would have those things that bacteria can feed on. Yeah. In general, darker roasts of coffee are, let me make sure I get this right, are less acidic because the acids get broken down, and lighter roasts that have that kind of fruitier taste are more acidic. Urine's probably good though. If you drink a lot of urine, you can not worry about your teeth there. So bodily fluids have very specific pHs for the things they have to do, particularly blood. So blood is given at 7.4. It really is a small range of about 7.35 to 7.45. But it's really important that it stay in that range. So saying that blood is neutral is really not good enough, because if your blood was at pH 7, you'd actually be in trouble. That would be too acidic. You'd be in what's called acidosis. So your body has very careful mechanisms to keep your blood at that particular pH. We'll talk about in a second. Getting on the more basic side of the scale, you don't see a lot of food stuff, more like cleaning materials. They tend to have more of a soapy kind of bitter taste. And then as you get basic, you can see the stuff is just as corrosive, just as caustic as the acid side. So things like oven cleaner, sodium hydroxide, ammonia are not, not any friendlier to your skin than stuff like hydrochloric acid.
Are you using jellyfish stings?
Jellyfish stings?
Yeah, like stuff for-
Yeah, I don't know the physiology of jellyfish stings. Does anybody know what's going on there? But I assume, yeah, that there's some sort of, that any of these like things on the extreme sides of the scale are good at breaking other molecules down. They tend to be able to react with other molecules and do stuff with them that we'll see like in the next few weeks when we do some of the biochemistry stuff. So yeah, it makes sense that those things would break down whatever other types of molecules. Things like, say, like baking soda is good for odors. Sometimes people like keep it in your fridge, and that's one of the reasons is that that can react with the whatever the organic molecules that are causing those odors and cause them to not smell anymore. We were trying to think of the other day some of the cooking uses of these. So baking soda is a good one. Does anybody bake cookies, bake stuff? So what happens if you don't put enough baking soda in? So that's part of it. Baking soda, when it reacts with acid, gives off carbon dioxide, which makes bubbles and kind of makes stuff rise a little bit. So it's partially a leavening agent. There's something else too. It actually has to do with pH. So baking and cooking is often pH specific. And the browning reactions, the reactions that make things turn brown and give that sort of yummy browning flavor, those tend to go better and proceed faster at higher pH. So adding baking soda to your cookies or whatever you're trying to bake will also help with browning. And if you don't add enough baking soda, even on purpose, if you don't use baking soda, use other things instead, you'll get very, very light colored results. So if you're looking for like really pale sugar cookies that don't brown, you're probably not going to use as much baking soda as you would with, I don't know, chocolate chip cookies or something where you want more of that brown flavor. To take that to more of an extreme, pretzels, everybody know what pretzels are? They're like bread, but they're like brown on the outside. So they get that dark brown outside with that specific pretzely flavor by, sorry, that was not a great description of pretzels, but next time you're at the store, ask people what a pretzel is. If you don't know, I'll tell you. But you take your dough and you soak it in a highly basic solution, and that makes the outside very, very basic, so that when you bake it, those browning reactions get kind of accelerated, and it makes that nice brown coating on your pretzel. Okay, so that's one of them. And then the other one we came up with was, besides the browning reactions, if you have ever made dough out of corn, dried corn, it's called masa. What you do is you take this dried corn and you soak it with a really strong base, calcium hydroxide, and that process is called nixtamalization, and it breaks down the corn and turns it into that delicious dough that makes all that good stuff. So that's another application of bases in cooking, but we don't usually just eat basic stuff. While we're talking about food, and there's also, we should clear up a big misconception about pH in food. So your body has to maintain this pH really, really carefully, and we'll talk about how it does that in a second. But a lot of people believe that the pH of your body is actually affected by the foods that you eat. So that if you eat acidic foods, your whole body is going to become more acidic, and that's a problem. So you'll often see foods marketed as like pH balanced or something like that, and that is all nonsense. Because think about what's happening. Every time you eat food, where does it go? Your stomach. And what's the pH of your stomach? Super acidic, like 1. So anything you put in your stomach automatically just is really acidic. So by the time it gets all metabolized out in your body, that has no effects on like the pH of your blood or other pHs around your body. So anybody trying to sell you stuff on the pH of the food that you're eating is kind of full of crap.
So these high alkaline diets are that's what you're referring to?
Yeah, right. So, well, there's a whole bunch of, there's like a whole
Yeah.
collection of nonsense that it all involves. Exception would be if you're trying to solve stomach problems because your stomach is too acidic. So that totally makes sense, right? Because if you've got too much acid being produced in your stomach, that could cause discomfort, things like reflux disease, heartburn, that kind of stuff. That certainly makes sense because that's caused by that stomach acid going places it's not supposed to go or going, doing things it's not supposed to do, having too much of it. So you can take medications like proton pump inhibitors and other types of things that actually stop that. And you can also change your diet that way, because if you eat more acidic foods, certainly that's going to affect the acid in your stomach. But that's not going to like make its way into your bloodstream and affect the other things going on in your body.
It will affect your urine?
Well, sure, depending on what it is and how it gets metabolized, depending on what's being metabolized, sure. All right. So that's pretty much acids and bases. The last thing we're going to look at is something called buffers. Buffers are solutions that maintain their pH even when more acid or base is added. So you've probably heard that term before, buffers or buffering solutions. Things like eye washes and those kinds of chemicals are often buffered to maintain a particular pH. It doesn't have to be neutral. A buffer solution can be highly acidic or highly basic, but the key to the buffer is that it maintains its pH. So if you add more acid to a buffer solution, you don't change the pH. Where if you add acid to water or to some other neutral solution, it would make the solution become acidic. So it keeps the pH where it is. And the way that that works is pretty interesting, but for time and just because it's not in the objectives, we're not going to go through it right now. But if you're interested, the book has a nice explanation of it. It uses weak acids as a way of like kind of controlling and scavenging the excess hydronium that occurs. But these are really important in a lot of systems, particularly in biology, because like we said, all these biological reactions require this really specific pH. So does anybody know what molecule is mostly responsible for controlling the pH in your blood? Well, hydrogen is always, yeah, it always is responsible for the pH, but what contributes to more or less hydrogen in your blood? Yeah, it's carbon dioxide. So carbon dioxide, when it dissolves in water, makes carbonic acid, H2CO3. And then carbonic acid, in turn, can react with more water to make bicarbonate ion and hydronium. Since hydronium or hydrogen is the source of acidity, that means that the more carbon dioxide that dissolves in the blood, the more hydronium there's going to be, and the less carbon dioxide that's there, the less hydronium there's going to be. And because of the weak acid thing that you can learn about if you want, carbonic acid is this weak acid, and so this acts as a buffering system to maintain the pH. But if there's not enough carbon dioxide in your blood, you can actually screw this up and not be able to control your pH properly. So looking at those reactions, if you were to remove carbon dioxide, would you expect the pH to go up or down? pH would go up, right? Because carbon dioxide is causing the acidity. So if there's not enough carbon dioxide, that means the acidity is going down, which means the pH is going up. So when does that happen in your body? When are you losing too much carbon dioxide? Yeah, if you're hyperventilating. So you know if that, like if you're breathing really, really hard, what you're doing is you're exhaling too much carbon dioxide, and there's not enough ending up in your bloodstream, and that's going to increase the pH of your blood and start to, you start to feel lightheaded and stuff, which probably has to do with the oxygen as well. So you need to kind of calm down, breathe slower, so that the carbon dioxide can better balance into your blood and control that pH. We'll see some buffers today in lab. There are some things that we eat, mostly when we eat things, other types of biological products are often buffering. So things like milk can actually, milk is not basic, but milk is buffering, so it can help control your acidity in your stomach. Yeah. So a couple things could happen, but the main problem is you would go into what's called alkalosis, which is meaning that your blood has too high of a pH. And that's not the only way you can go into it's called respiratory alkalosis. There's also metabolic, which is your organs doing it. But really, I don't know all the specifics of it, but all those enzymatic reactions and those processes that depend on your pH being in this really narrow range are no longer going to work. So whether it's neural pathways or enzyme activity, various things are going to stop working because the pH isn't right. Does anybody have more specific examples? Any physiology folks who know? Because I don't. But yeah, sorry, just bad stuff. Bad stuff happens. All right, so that's buffers. I think that pretty much does it for acids and bases. So any more questions about the acid-base stuff? All right. Our next topic then is to, actually I'm going to change files. Start fresh here. And we're going to talk about organic chemistry. Somebody just go blah. No, come on, it'll be fun. So to do that, we hand out these model kits. We'll be using these a bit over the next few days, so please put them back at the end of class. I think we have enough for like 2 per table here. All right. Has there ever played with these kinds of things before? Maybe. Yeah. All right. So we're going to go from the very mathy to the very visual. And this stuff can be a little tricky, but not for the same reasons. So this is much more about, can you visualize things in 3 dimensions? Can you flip things around in your head? And one thing that's going to help us a lot with that is to actually build them so you have physical things to look at instead of just trying to imagine what this would look like in 3 dimensions. So organic chemistry, for our purposes, is going to be defined as the chemistry of molecules based on carbon. There's going to be lots of other molecules here too, or lots of other atoms too. But the word organic is associated with life, and it actually comes from a long time ago. There was the split where it was believed that molecules produced by living things, plants and animals, would always be completely different from molecules produced by non-living things, minerals. And there was this idea that like if something wasn't living, there was no way that it could ever produce the same molecules as things that were living. Like there was some innate difference. And now we know that's not really true. There's organic minerals and it's all kind of just together. But we keep this term to talk about molecules based on carbon. And we're usually, not always, but we're usually, especially in this class, talking about molecules that have something to do with interacting with living systems. So things like medications, things like the biological molecules we're going to see in a few chapters. Those are all going to be based on organic chemistry. All right, so to figure out what these things look like, let's go back and review a little bit about carbon. Carbon, of course, is C. How many valence electrons does it have? I heard it somewhere. 4, yeah. Spell it correctly. 4 valence electrons. And that means how many more does it need to have a full shell? 4 more, because we know 8 is a full shell, right? All right, so we've talked about this before. Carbon doesn't really make an ion the same way that we think about the other atoms around it making ions. But what it does do is bond with other atoms. So we've looked at something like this before. If we take hydrogen, which has 1 electron but wants 2, we can have those sharing a bunch of electrons so that the carbon now has 8 total and each hydrogen has 2. And the way that we usually represent that is not with the dots, but with lines. So that's showing 2 electrons being shared between carbon and each hydrogen. This molecule has a name, methane, and it's the smallest organic molecule. So everybody, well, not everybody, but every pair or so of people build a model of methane. And this is how we're going to do it. Use the little black pieces, but be careful because some of them are a little bit different. I just noticed this. So there's some that have extra holes around the sides and like a little ridge. Don't use those. Use the symmetrical, more symmetric ones that just have 4 holes in them. Put a stick in each one, and then put one of these little round balls on the end to indicate a hydrogen on each one. If you use the same, if you can, depending on your kit, if you can find 4 of the same size sticks, that'll make a nicer model. There's 2 different sizes in there usually. All right, once you're done, you should have something like this. I'm going to put a picture up here too. All right, so you got something like this? That's what your model looks like? All right. So how is that different now from what we drew here? How? Yeah, like if you were to, if I hadn't drawn that and I said draw a picture of this molecule, you probably wouldn't draw it like that, right? Because it, like you can put this in a scenario where it kind of looks like that, but you'd probably think of it more like this, right? Or this kind of pyramid look to it. So this has a different structure from what we've drawn there, and we need to reflect that on paper. The way we do that is using a three-dimensional notation to show that that's the actual structure. So that actual structure is called a tetrahedral structure. Or a tetrahedral geometry. A tetrahedron is a regular solid that has 4 sides. It's kind of like a pyramid with a triangular base, but every side is equal, every point is equal, every edge is equal. It's called a tetrahedron. So if you imagine the hydrogens on your model, you lose a hydrogen? There it is.
I think.
Okay. If you imagine these hydrogens being connected by lines, that would give you that shape of a tetrahedron. So let's draw it. Now, depending on how good you are at fancy 3D drawings, you might draw it however you might draw it. But a lot of us aren't so great at 3D drawings, so there's a way that we can do it and make sure that we're expressing the right thing without being too fancy. So put your model in kind of this kind of a geometry, so that you've got 2 of them going over to the, or I'm sorry, 1 straight up, 1 over to the right, and then on the left side, 1's coming out at you and 1's coming back. Kind of set it on the desk like that so you're looking at it. I'm going to move it a little bit so we can see all 4 hydrogens there. Something like that. I'll cut this out so we can put it in the notes. So in this example, we've got the carbon here, hydrogen, 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 hydrogen. So carbon going to these 2 hydrogens are just going to be straight lines because they're in the same plane. Just like the water structure, they have that kind of bent geometry. The tricky part is the other 2 because we have to express that 1 is coming out toward us and 1 is going back away from us. And the convention that we use for that is on the one that's coming out toward us, we draw this wedge-shaped bond like this. And then the one going back, we draw a dashed bond like that. And that represents 1 coming forward and 1 coming back. So drawing that on just over here, more regular size, it's going to look like that. Now you can do this in any direction or any way you want. We could draw it the other way. And this is called the dash wedge notation. The dash and the wedge are always on the same side, just as it would be here. So you've always got 2 bonds in the plane of the paper, meaning like flat on the paper, and then 1 going back and 1 coming forward. And that's the shape of these molecules. So since these molecules are based on carbon, we can expect that we're going to see this shape a lot. Okay. Now that we've got that, let's start looking at the simplest class of organic compounds, which are called alkanes. Alkanes are molecules with only carbon and hydrogen. And only single bonds. So they're just carbon and hydrogen and just single bonds. And we're going to learn some of their names and look at some of their structures and use them to learn the most common way of drawing structures in this area. We'll make a little table of the alkanes. We're going to have their name, the molecular formula, then we're going to look at 3 different ways of drawing the structure. The first way is the kind of normal way that we know how to draw structures, which we're going to call Lewis structures, just to separate it from the other types of structure. We're going to look at the condensed structure or condensed formula. And then finally, the line structure. And these last 2 are the new ones. And I'm not going to explain them quite just yet, especially the last one. We'll see how far we get. We may just work on this more on Thursday. But let's start looking at some of the members of this. So one we've already talked about, and that's methane. The molecular formula of methane is CH4. Its Lewis structure is like this. We could also draw it with the dash wedge notation. We're going to keep it flat like this just because it's easier to see the differences that way. The condensed structure is also CH4, and there is no line structure.
So the condensed and the molecular formula is the same.
No, so just for methane. So let's leave that one, and we'll go to the next one, which makes it a little bit more interesting, which is ethane. Each time, this is going to go up by 1 carbon. So now we have C2H6. And our Lewis structure now looks like this. 2 carbons connected. With 6 hydrogens. And now you're going to see a difference in the condensed structure. Which is CH3CH3. So the way a condensed structure works, or the reason for it, is that the molecular formula tells us how many carbons and hydrogens are in there, but it doesn't tell us how they're connected to each other. The condensed formula, or the condensed structure, still kind of looks like a formula. It's still easy to type out on a computer and all that, but it tells us more about what's connected to what. The reason it's called condensed is that the hydrogens are condensed down onto each carbon that they're connected to. So we get a sense of how the carbons are connected to each other, and then we just say, all right, well, the hydrogens are condensed down onto whichever carbon they're connected to. The line structure for this one is just a line like that, and we'll talk about that later. Just leave it for now. All right, the next one in the series is propane. Propane is C3H8. Structure looks like that, and you can see it's already starting to get a little bit tedious to draw the Lewis structures. And this is the reason that we don't use them much in organic chemistry is as the molecules get bigger and bigger, it just takes forever to draw out all these bonds and hydrogens and everything. So that's why we use these other types of formulas. So the condensed structure here is going to be CH3, CH2, CH3. And we can see how this first carbon has 3 hydrogens attached to it. The second one, 2. So that's the CH2. And then the third one, 3 again, CH3. And for this one, the line structure looks like this. Fourth member of the series is called butane. And I want you to see if you can fill in the rest of it. Yeah.
Oh, is there not?
There is not, right? So see if you can fill in the rest of it for butane, following the pattern that we've already established with those first three. I'll give you a hint. It's easiest if you start with the Lewis structure. Draw out the full structure, and then you should be able to get the formula, the condensed structure, and if you want to try to take a guess at the line structure, try that too. We'll get into those more in detail on Thursday. All right, you think you got something that makes sense? I bet you got it. So did you come up with C4H10? Maybe? Yeah, okay. If not, that's okay. Good first guess. And then to make this Lewis structure, we got to draw all this stuff out like this. Whoa, can't even get that one on the page here. So then our condensed structure looks like CH3, CH2, CH2, CH3. Yeah? Okay, and then if you give the line structure a try, maybe add something like that.
Are we supposed to not do the line structure?
No, right. But if you could maybe try it, you can maybe figure out what's going on with the pattern of the line structures there. Anybody want to give it a try? What's going on there? How do these line structures work? You can figure it out. Take a look at those four, and the molecules, remember those are molecules, they're representing molecules. It adds a line, so where are the carbons in the line structures? What do you think? Yeah, exactly. So there's a carbon at each end of the line, and then whenever they meet in one direction or the other. So every time there's a little inflection point, there's a carbon. So here's 1, 2 carbons for ethane, 1, 2, 3 carbons for propane, and then 1, 2, 3, 4 carbons for butane. Okay. All right, we're going to get into those in a second, but, well, actually, we won't get to it today. We'll just wait till Thursday. But let's finish. Let's do a couple more entries on this table. So after butane, we've got pentane, and then hexane. And let's see if you can draw them before me. So we'll draw them together, but see if you can just do it without looking up here, following that same pattern. So you can see these Lewis structures getting pretty tedious here. Even the condensed structure is starting to get a little bit tedious. And that's why we start using these line structures, because they're so much faster and easier to draw. All right, so that's the first 6 or so. I'll give you the names of the rest of the series. We're not going to draw them all out in structure form right now. But the other alkanes that you should know the names of are heptane, octane, nonane, and decane. So they continue that same pattern. Up to 1 through 4 have special names that you may need to do a little work to remember. 5 through 10 are your typical prefixes for the numbers with ane at the end. So pent, hex, hept, oct, non, and dec, plus the ane prefix. But those first 4 are totally different: methane, ethane, propane, and butane. So that may take a little work to remember. All right, Thursday we'll get into the line structures and drawing all kinds of different bigger structures, talking about isomers, and maybe get into functional groups a little bit. And then that'll be the end of what we do for the first exam on Tuesday. All right, so that'll be it for now. I'll see you in about 15 minutes for lab.